Alrighty. Good morning, everyone. Welcome to another beautiful morning of Pre-Calc 2. So a couple of notes, some things coming up. Our Chapter 11 homework, I did make that available yesterday. I did not realize I did not have that open in my math lab. I meant to have that available on Monday, but I did open that up pretty early Tuesday morning. It's clearly morning. And that our combined Chapter 7 and 11 test, we're going to do this take-home thing again. Hold on one second. And it's going to start Wednesday the 29th, so I'll make that available at 12:01 a.m. I'll also have the review available. It's getting crunch time, so it's pretty hard for me to get these reviews available super early. But I'll at least have it available Tuesday the 28th. I know most of y'all like taking this the last 1 or 2 days anyway, so you still have time to work with the review. It's not like you won't. And it'll be the same situation as before. I'll give you 2 attempts. I'll grade your best attempt only, not really doing partial credit unless like you put a period in place of a comma or vice versa, something like that. I'm not giving partial credit. It's right or it's wrong, given the conditions. And that our final, I'm thinking, is going to be Wednesday the 6th, and this final exam is going to be a 1-day only situation. I'm still working out exactly how I want to do this. I'm trying to decide if I want to have this like the previous tests where it's the test 2 and 3 where it's my math app only, or if I want to have more of a traditional component to it. I'm thinking I want to do a hybrid, but I got to make my decision soon. You will know, of course, in advance, but there's likely to be an actual handwritten portion that you'll have to upload to Canvas for me. So we'll see if that actually happens. It might be the Monday after, but I think I'd rather do it this Wednesday, just in the interest of the several different things, and grading is going to be fun. So, I don't know why that won't pop up now. Here we go. So, picking up where we left off in 11.1, so 11.1 we said was on sequences, which is just a kind of a sequence. I like to say a series of numbers, but then that might confuse you and think it's a series, which is what we'll talk about in the next section, or what we already started talking about kind of. But a sequence is just a bunch of different numbers that have some type of relationship between each other, a pattern. There is an equation that you have some inputs, and then your output is a term of a sequence. So we have a first term, a second term, a third term, all the way up to an nth term if it's a finite sequence. If there's infinitely many terms, then n would be unbounded. And we practiced doing some of these where we gave you a formula for the sequence, and we found 4 or 5 terms. We saw alternating sequences. We saw recursive sequences where the next one was based on the previous one, or you could even have sequences that are based on several previous terms. And there is a whole world of math that involves this kind of recursive relationship, especially when you get into something called differential equations, which leads to difference equations. And that last one, it sounds like it would be really simple, but it's not. It's a simple idea, but it opens up, again, a whole new world of mathematics. But anyways, we did factorial notation. We showed how we could do problems that a calculator can't even handle. And then we started with the series notation, the summation notation that leads to series. We said that the number you see on the bottom of this little symbol is your starting index. The number you see on the top is your ending index. And then the thing to the right of it would be your formula, which you're plugging the number into for each term. But now, when you have this symbol, instead of just saying, here's the first term, here's the second term, here's the third term, you're going to add them all together. And we practice some of that, and that takes us to where we left off with C. And this is going to be the sum. So when you see that symbol, you say the sum from I equals 1 to 8. And the formula for our sequence will be 3. Now, this is vastly different than any of the sequences we've seen over the last bit of time for this section, because all the other sequences have this I here, I plus 1, or I squared, or all the other things, -1 to the n over n plus 1. It doesn't matter whether that letter's an n or an I. It's just your variable. It's just your input variable. Now there is no I, which means there's nowhere to plug in the 1 or the 2 or the 3 or the 4 or the 5 or the 6 or the 7 or the 8 into this, which means this is a constant sequence. It means that every term is the same. Every term's 3. It's just like if you have the equation y equals 3, there's nowhere to put an input, so the answer, the output's always 3. So this is going to be equal to, well, hold on, let me just show you what the first terms are. Undo. So A1 would be 3. A2 would be 3. A3 would be 3, et cetera, all the way up to A8, which should also be 3. Every single term of the sequence is 3 because there's nowhere to plug the input variable. So the sum would be A1 plus A2 plus yada, 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 all the way up to A8, because they said to add the first through the 8th terms, which is just 3 plus 3, and I'll write the number of 3's out appropriately. Here's the 4th one, 5th one, 6th one, 7th one, 8th one. It's really hard to say different numbers and write the same one over and over, believe it or not. So we have 8 of these 3's, which is really just 8 times 3. You can even rewrite it that way if you like, which is 24. Most of us would have just gone ahead and said it was 24, understandably. But I just thought that was a cool little memo. I'm going to have to come on, let me highlight everything. There we go. Oh, I can drag it somehow. If I don't have this thing put down far enough at first, it goofs this up really bad. It's annoying. There we go. Ha! I figured it out. Insert blank page works. Okay, let's go ahead and get some space. There we go. D. The sum, let me put that a little lower, from I equals 1 to 4 of -1 raised to the I, so there's going to have an alternator in this, over I. And like I said, these i's can be any letter in the world as long as they match this letter. So I might say the sum from n equals 1 to 4, and that would be -1 to the n over n. Again, these letters just have to match this letter. So we should first figure out what the first 4 terms are the first, second, third, and fourth. So A1, we're just plugging 1 into this, so that would be -1 raised to the first power over 1. I'll show the plugging in, which -1 to the first power is -1, over 1 is -1. So the first term is -1. The second term would be -1 to the second power over 2. Again, in red, I'll show what we plugged in, which is +1 over 2. So the second term is a half. The third term, excuse me, would be -1 raised to the third power over 3. Which is -1 over 3. The fourth term would be -1 raised to the fourth power over 4. And again, the red is showing what we're plugging in. A negative to an even is a positive, so that's 1/4. So therefore, our sum from I equals 1 to 4 of negative 1 to the I over I would be the first plus the second plus the third plus the fourth term, which is negative 1 plus a half plus negative a third plus a fourth. Well, we're going to have to get an LCD here. Between 2, 3, and 4, our LCD is 12. The negative 1 is going to become negative 12 over 12, because you're going to write that denominator as a 1. 1 goes into 12 12 times. 12 times 1 is 12. Then plus. The 1/2, 2 goes into 12 6 times. 6 times 1 is 6, so that'll be 6/12. Then a minus for the plus and negative. 3 goes into 12 4 times. 4 times 1 is 4, so that's 4/12. Plus 4 goes into 12 3 times. 3 times 1 is 3, so 3/12. So that was just us getting an LCD, something we should all be capable of. Negative 12 plus 6 is negative 6. Negative 6 minus 4 is negative 10. Negative 10 plus 3 is negative 7. So negative 7/12 is our answer. So finding a series, which again is what this is basically known as, we're going to talk about more specific series in the next coming sections, but a series is just a sum of terms. So that's exactly what we've been doing so far. When we're adding a bunch of terms, that's a series. So a series is adding up a sequence where the sequence has to be defined. Now you can have recursive sequences, you can have non-recursive sequences, and they can lead to series that are recursive or non-recursive. Like we said, that Fibonacci sequence, that was basically a series, arguably, because you just keep adding the previous two numbers. I was coming back to this for a reason. So what we want to do for our last type of example, instead of being given, I've been outside too much, I'm all stuffed. Okay, instead of actually being given the sequence and told the number of terms that we're going to add, let's flip the script on this and let's be given the individual terms and let's see if we can write the series. Let's see if we can figure out the pattern, if we can figure out what the sequence is, and then what the specific terms are. You know, where are we starting, the first and going to the fifth? Are we starting at the 17th and going to the 19th? So let's try that out, because that is, I think, for a lot of people, the more challenging type of problem, but also very critical to understand. So for example 6, we're going to write the given sum, not as, in summation notation. Where's my undo? In other words, as a series. I know I'm begging the question with that because I haven't officially defined what a series is, but I have said it a couple times. So for A, we're going to have 1 squared plus 2 squared plus 3 squared plus data 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 all the way up to 13 squared. So our goal is to ultimately write this, again, you know, with having something like that, an I, a number down here, a number up here, and then a sequence here, some formula here. That's our goal. So we need to first identify what A sub n should be, which is the sequence. What's the formula to get the 1 squared, the 2 squared, the 3 squared? Then we need to figure out where we start and where we end. The 1 through the 13 are the clues for that. See, the consistency here is that every single one of these things is being squared. Each one of this 1 squared gives us the first term of the sequence. This 2 squared would be the third term. The 3 squared would be the third term, etc., all the way up. And I'm trying to demonstrate, or illustrate, excuse me, that there's going to be 13 terms. So again, each of these counts as their own entity to try and hint at what the sequence should be. So this right here says there should be the last term is the 13th term. And this right here says that the first term is the first term. So let's say I didn't have the 1 squared and the 2 squared. Let's say I started this at the 3 squared. That would be a good hint that the first term is supposed to be the third term. The first term in our series is the third term of the sequence. And then what else do we see? They're all being squared. These 3 little bits of information are all we actually need to be able to tell that this should be equal to the sum from I equals 1 to 13, because the first is the first, the last is the 13th. 13 squared. We started at 1 squared, we ended at 13 squared. Now each of these terms is being squared. That's completely consistent from them. So I would just take the sequence value, which is I, and square it. And that's it. That's all there is to it. And if you don't trust this, go back and use I squared to write out 13 terms, 1 squared, 2 squared, 3 squared, 4 squared, etc. Add them up, and well, I mean, you don't even have to add them up because we never told you what the value was, but you can see that when you separate this as the individual terms, it would be the same thing. Now, I was very nice here with this problem because it's our first one, and I gave us the 1 squared, the 2 squared, the 3 squared, the etc. An alternate version of this, I could have written this as 1 plus 4 plus 9 plus 16 plus 25 plus all the way up to 169, and you would need to recognize these are squared numbers. Every single one of them is the square of another number. That's 1 squared, 2 squared, 3 squared, 4 squared, etc. So that would be an extra step that you would have to take as the student. And I'm not saying you would never have to do that step. That's why I've just labeled it as an alternate form of that example. Oh my, I learn something new every day. I can change between just black and red on this. Between that and the insert page button, I'm gold now. All right, let's do another one of these. 1 plus 2 plus 3 plus 4 plus all the way to 52. Some would argue this problem's easier. Some would argue it's more difficult. I really don't agree with that second one. I think it's easier, but everything's relative, right? Okay, so this is a 1, this is a 52, and it seems like each term is just adding 1. So I think that's a pretty good clue that we're going to start in terms of the sequence with 1 and end with 52 in the sequence. So we'll go from 1 to 52. Now, what else is happening in these? This is just 1, this is 2, this is 3, this is 4. You could use a recursive formula, but then you'd have to define an a sub 1, and then a sub n would be a sub n minus 1 plus 1. That would work. But I didn't ask for a recursive one, and again, I wouldn't count it wrong on a test if you did that. What they want is just to do this in simple terms of I. I mean, this is just the first index, this is the second index, this is the third index, so why not just have the sequence be I? Would that work? Would this work? From I equals 1 to 52, remember first, last, of just I. So the first term would be 1, the second term would be 2, the third term would be 3. Yeah, that actually works. Wrong button. I shouldn't use my pen to go up there. I should stick with the mouse. So B is actually an easier problem than A. It's an easier formula, at least. Let's switch that up for C. Let's make it more harder. 7 plus, and again, I don't have to write it this way. I could write 49 over 2, but I'm going to write 7 squared over 2. So again, I could write 49 over 2. I don't have to be so explicit with the 7 squared. Then I'll go 7 cubed. So once again, I could actually write, what's that, 343? But I'm going to be nice just to get us to the point quicker. And then plus 7 to the 4th over 4 plus da-da-da-da-da. And let's go to 7 to the 9th over 9. So again, the emphasis there I was trying to say was, I don't have to label these with bases and exponents. I could say, you got to figure out that there's a pattern there. Oh, that 49, well, that's 7 times 7, 343, 343. Maybe if I took 49 times, yep, that is, so it's 7 cubed. And then you can start picking those pieces of the puzzle out and putting them together. Okay, so this one is a little quirky, just I think because of the first term. If you ignore the first term, the answer is even more obvious, at least to what the sequence should be. There's a top and a bottom of this, so in the sequence, it's going to have a top and a bottom. The top, it seems like we're just taking a 7 and then raising it to a power that's incrementing by 1. So we can probably use the index for that. So we can just say that's 7 to the I in the top. In the bottom, 2, 3, 4, blah, 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 9. Since that matches the exponent, we can just say the bottom is also the index. But what might throw you off is you'll say, well, that doesn't fit the first term because I don't see a denominator, nor do I see an exponent. Well, the thing about denominators that you don't see is that they're a 1. The thing about exponents that you don't see is that they're a 1. So I just want to point out the first term, if you want to be more explicit, is really 7 to the first over 1, so that the power matches its appropriate term, the bottom matches its appropriate term. So this is the first term in the sequence. This would be the 9th term in the sequence. And again, each of these a sub i's seems to be 7 to the I over I. Meaning that this sum can be written with the summation notation going from 1 to 9. And then just the AI, 7 to the I. There's a little dot there I didn't mean to have. Over I. These types of series, or even just sequences, whether they're being summed or not, are very, very common when you get into Calc 2. Calc 2, you're going to deal with a lot of infinite series. I sometimes like to spoil topics ahead of time just so that you know what you're going to get into. You're going to ultimately learn how to take some normal function like a polynomial or a trigonometric function like a sine or a cosine and turn them into an infinite series. So a lot of computers don't like handling sines and cosines, but you can turn them into an infinite sum of polynomials, things like x and x cubed and x to the 5th, or x squared and x to the 4th. And they don't have to be the even or odd powers. It's just how it works out for those two functions. And you can approximate the functions in a local region. And what it turns out is that a lot of those approximate functions, these infinite things, have these typical powers with something in the top and the bottom, or they'll have a -1 to the I in them. This stuff is seen a lot. So we are setting you up for a later calculus class with this stuff. All right, so that's why I've said I'm temporarily skipping over chapter 10, because chapter 10 is just formulas, whereas this is kind of a bigger concept. With that being said, let's move on to 11.2. Make sure I have another page. There we go. 11.2. arithmetic sequences. So 11.2, we're going to do arithmetic sequences. And 11.3, we're going to do geometric sequences. And you might think that the geometric one has to do with geometry and the arithmetic ones have to do with arithmetic, and quite honestly, no, that's not the case. I'll kind of spoil this. It's all about whether you're multiplying or adding to get something else. That's all it really is. I don't know why they decided to give them the name arithmetic and geometric. It is what it is, though. It's just a name. Not all names in math are perfect. So what is an arithmetic sequence? Let's start there. An arithmetic sequence, oops, I did that too soon. Oh, why did I do that? An arithmetic sequence is one in which, a mathematician's favorite phrase, each term after the first is a constant difference from the previous. This difference is known as the common difference, and we denote it with the letter D. So what does it mean for a sequence to be arithmetic? It means that you can just add a number to get to the next one, and that number is always the same. So if your sequence goes 1, 4, 12, 30, 100, that's not an arithmetic sequence because the gap from term to term is getting bigger and bigger. Again, I said something like 1, 4, 10, 30, 100. So that first gap was like 3, the second gap was like 10, then 20, and then 70. So that difference was changing, it was getting bigger, and it could get smaller as well. So that's not arithmetic. An arithmetic sequence is one that goes like 1, 5, 9, 13, 17, where the difference between them is 4 each time. And you can very quickly find the next one and the next one and the next one by just keeping on adding the same number over and over, or subtracting in some cases, because adding and subtracting are really the same thing. So again, an arithmetic sequence is one in which the next term is the previous term plus a number, and that number doesn't change. So we actually dealt with several arithmetic sequences in the last section. We just didn't call them that, but we also dealt with several that were not arithmetic. So when they are arithmetic, we can break them down and talk about them in a slightly different way. We can also use a formula to find the sum of them without actually having to list every single term and then adding them up. There's a formula we can use, which is going to be super convenient when we want to add up a sequence of, say, 50 or 100 or 10,000 terms, and we don't want to find out what all 50 or 100 or 10,000 of those terms are. All we'll end up needing is the first and the last. All right, so for example 1, let's find the first 5 terms of the arithmetic sequence. Whose first term is 3, and a sub n is equal to a sub n minus 1 plus 11. So we're going to find the first 5 terms, of the arithmetic sequence who has a first term, or that has a first term, that is 3, and then it has a recursive relationship that the next term is the previous term plus 11. I feel like this right here is enough to say that it's arithmetic. You're just taking the previous term and you're always adding 11. That right there says it's arithmetic. This right here, this 11, is probably your D. All right, but we were just asked to find the first 5 terms, so a sub 1 is, well, they gave it to us, right? It's 3. First term is 3. That was easy. A sub 2, we are now going to need the recursive relationship. That'll be a sub 1 plus 11, which was 3. And 3 plus 11 is 14. The next term, the third term, would be the second term plus 11, which is 14 plus 11, and that's 25. The fourth term would be the third term plus 11, which is 25 plus 11, and that's 36. And then our last term, our fifth term, would be the fourth term plus 11. That's 36 plus 11, which is 47. So it's not very difficult to find the next term and the next term and the next term for an arithmetic sequence, because you really just keep adding the same number over and over and over. And I could give you this problem in several different ways. I don't even have to give you the sequence. I can just say that the D is 11, so you take the first term and you add 11 to get the second term. Then you add 11 to get the third term. You add 11 to get the fourth. You add 11 to get the fifth. There's nothing crazy going on there. If you think there is, you're overcomplicating things inside your mind. So how is this helpful? What can we do? How can we extend this idea? Well, in general, if the first term is known and the constant difference D is known, the nth term of the sequence is, there's a nice little formula, A sub n is equal to A sub 1 plus n minus 1 times D. This is a formula that I suggest you memorize. This is only for arithmetic sequences and series. And that is a D at the end. This formula is not something that we're pulling out of thin air. All we're doing is adding D over and over and over and over and over. So if you start with the first term, so the nth term is the first term plus that constant difference plus the constant difference plus the constant difference plus the constant difference, however many of these you're supposed to add. Now let's just come up with a simple example. Let's say I want you to find the fifth term. If you know the first term and you need the fifth term, that means you would have to add that D 4 times. Because to get to the second term, you add it once. To get to the third term, you add it a second time. To get to the fourth term, you add it a third time. To get to the fifth term, you add it a fourth time. It's always one less than the terms you need. So this right here, there is one less than the term you need, one less than n. And guess what? N minus 1 is 1 less than n. And adding the same thing over and over and over just means you're multiplying it. You can take the D times however many of them you have, which is 1 less. So again, you start with the first term, and you're just adding D over and over and over. How many times do you add it? 1 less than the term you're trying to get to. If you're trying to get to the 17th term, you're going to add it 16 times. If you're trying to get to the 50th term, you're adding it 49 times. And you can see that in example 1. We added 11, 1, 2, 3, 4 times. So example 1, let's prove this works. A sub 1 was 3. The D, the thing that we just added each time to get to the next one, was 11. So A sub 5 should be A sub 1 plus 5 minus 1 times the D, which is 11. So that's 3 plus 4 times 11, which is 3 plus 44, which is 47. It works. Again, you're adding the first term plus d a bunch of times. If you're adding the same thing a bunch of times, just multiply that thing by something. What are we multiplying by? One less than the number of terms we're trying to get to. So you can actually call this right here, example, let me go back to black, 2a, to find the requested fifth term. So example 2a is just proving that it works by using the example we've seen, example 1 already. So we were requested to find the fifth term. Here is us finding the fifth term in a new, exciting way. Now we'll do it with a completely different set of examples. So a sub 1, I said examples, I meant to say values. A sub 1 will be 40, and the d will be -8. And we want to know what is the 11th term. Nobody said d couldn't be negative. It just means we're subtracting the same thing over and over and over. Subtracting is adding the opposite of. So subtraction's fine. So we do not need to find the second term. We do not need to find the third term. We do not need to find the fourth term to get to the 11th term ultimately, because we're just going to keep adding -8 each time. How many times do we add -8? Well, to find the 11th term, we're going to add it 10 times. So our formula, this a sub 11, should be the first term, a sub 1, plus, now we're finding the 11th term, so that's 10. 10's the number there. I was supposed to write 11 minus 1. Times the d, which is -8. Well, our first term was 40. I don't know why I keep writing the first term there. It's fine. Didn't do anything wrong. Plus 10 times -8. So again, take the first term, add the d over and over and over. How many times? One less than the term you're trying to find. 10 times -8 is -80. So that's 40 minus 80, which is -40. So the 11th term is -40. If I wanted the 100th term, we could find it right now. We would have added -8 99 times. C, let's have our first term be 1. And let's have let's do this different. Let's say a sub n is a sub n minus 1, then a plus 2. And I'm going to ask, what is the 103rd term? So what do we do here? This is different, right? I gave a recursive relationship instead of what we saw before, where I gave you the first term and the d. So the 103rd term would just be the 102nd term plus 2. So again, the 103rd term would be the 102nd term and then a plus 2. But I don't have the 102nd term, do I? So I'd need to get the 101st term to get the 102nd. I need the 100th to get to the 101st. It's a big old mess, right? Well, we mentioned something earlier, that when you have a recursive relationship and it says that the new one is the old one plus some number or minus some number even, that's just telling you what the d is. So guess what? This right here says that d is equal to 2 because it just says to get the next term, you take the old one and you add 2. So if we want the 103rd term, we can now use the formula because we have our d and we have our first term. So a sub 103 would be the first term, which is 1, plus, again, the first term's there, plus n minus 1, so that's 103 minus 1, times d, which is 2. Now, if you don't recognize that the d is 2, what you would have to do is find the second term, find the third term, find the fourth term, and then say, hey, every one of these terms has a difference of 2, so boom, there's my difference. So that's an alternate approach if you don't remember this little detail here. All right, let's simplify. So that's 1 plus 102 times 2, which would be 204, and then adding that 1 would give you 205. So here's the little note I just mentioned. If you did not recognize that d is 2 immediately, you could say, all right, well, let me do a sub 2, which would be a sub 1 plus 2, which is 1 plus 2, and that's 3. And then a sub 3 would be a sub 2 plus 2, which is 3 plus 2, and that's 5. A sub 4 would be a sub 3 plus 2, which is 5 plus 2, and that's 7. So the sequence is going 1, 3, 5, 7. D is definitely 2 based on that, because 3 minus 1 is 2. 5 minus 3 is 2. 7 minus 5 is 2. It's a constant difference between each term of the sequence. So once again, if you did not pick up that the d is 2 based on the recursion formula, what you need to do is just express 2 or 3 or 4 of the next terms and then see that the difference of each of them is the same. So that's an option. All right, how are we on time? 30 minutes, plenty of time. So I mentioned at the start of this section that maybe you want to have to add the first 50 or 100 or 10,000 terms of a sequence. You would be really annoyed to have to do that by hand if I ask you for the sum of the first 10,000 terms of a sequence, because then you got to go and find the first, second, third, fourth, fifth, sixth, 100th, 1,000th, 9,999th, and 10,000th terms, whew, and then add them. That sounds like a job for a computer or a calculator, in my opinion. Well, yeah, if the pattern between them wasn't super simple, if it wasn't arithmetic. But it turns out, and it's a pretty fun proof, if you ever want to look into it. But what we can say is that, come on, the sum of the first n terms of an arithmetic sequence is. And we use the letter S for this, for sum, S sub n. So that's saying the sum of the first n terms. This is n over 2 times the sum of the first and last. So again, this is a fun little proof if you want to go to the internet or go to your textbook and check it out. I wish we had time, but we are definitely lacking in time because of missed time, so I don't want to rant too much. But this is a fun little proof. And what it kind of looks like is, and I don't know why I'm still in green, that's my bad. All right, so it doesn't matter. What this kind of looks like is it's the average of the first and last terms. I'll erase the circle in a second. But this part right here, this says A1 plus A sub n over 2. This is the average of the first and last terms. So the n is the number of terms, and then times the average of the first and last terms. That's really what's going on here. So I prefer to rearrange this in my own head to make this make more sense, or at least give it context. I've always written it this way, with the n out in front or even at the end, but not the n over the 2. I like the over 2 part to be paired with the parentheses, because this right here, the a1 plus a sub n over 2, is the average of the first and last, and then you're multiplying by n. And you can geometrically reason this, since we're adding the same number over and over and over, we should probably just be multiplying by however many times we're adding that. And if you average the first and last, that kind of common difference gets melded together. This is an amazingly convenient formula. But in order to use this formula, you have to know the sequence's arithmetic. Must prove or be told the sequence is arithmetic. So again, this is a formula you are supposed to memorize. Aren't those colors just great together? Green and yellow. Okay, so let's try this out. And I don't really want to keep that highlighted, but I would like to switch back to a pen, please and thank you. Example 3. Find the sum from I equals 1 to 25, and then the sequence will be 5i minus 9. Yes, minus 9. So we want to find the sum of the first 25 terms of the sequence 5i minus 9. Now, sure, you can go and find the first, second, third, fourth, fifth, blah, 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 all the way to 25th terms, and then add them up. It's time consuming. You don't want to waste that much time on a problem like this. And if I said to find the sum of the first 250 or 2,500 terms, holy cow, are you going to waste some time doing it that way? So we're supposed to be clever and recognize, hey, we had a formula for arithmetic series. Maybe this is an arithmetic series since we're asked for so many terms, and then maybe we can just use this formula and knock it out in way less time, proportionally speaking. So let's first show that this is an arithmetic sequence. In other words, we need to show a couple of the terms, first, second, third, show that there's a common difference between them, because this is not recursive and it's not just the last term plus another number. So we have to show that this is actually an arithmetic sequence, that there's a common difference. So let's get the first term, let's get the second term, maybe even the third term. A sub 1 would be 5 times 1 minus 9, which is 5 minus 9, and that's negative 4. A sub 2 would be 5 times 2 minus 9, which is 10 minus 9. Did I write something wrong? No, that's right. I don't know why I thought I read something wrong. That's on me. So a sub 1 is negative 4, a sub 2 is 1. You could show the third one if you like. You can also just find the third one after getting the d. So that would be 5 times 3 minus 9, which is 15 minus 9. And that's 6. Look here. Between negative 4 and 1, that says there's a difference of 5. You take the last one and add 5 to get to the next one. Between 1 and 6, that says that the difference is 5. I think that's good enough. If you want to show A4, you can. That would be 5 times 4 minus 9, which is 20 minus 9, and that's 11. And sure enough, the difference between those two numbers is 5. So I'd say that's pretty good. That's a little check mark that's next to that last one. It's just kind of poorly placed. So we know that our D is 5. That is one of the 2 important bits of information we need for this formula. Well, one of 3, arguably. So let's go back to the formula and see what else we need. Well, in this formula, we need the first term, we need the last term, and we need the number of terms. We know two of those things right now. We know the first term. We have the first term over here is -4. So a sub 1 is -4. That's important. We know the n is 25 because this is a 25. But we don't know the 25th term. How do we find the 25th term? Well, there's a couple of different ways. You could actually use the difference formula from earlier, this guy right here, and say, well, the first term, and then plus 24 times that common difference of 5. Or you could just use the fact that the sequence is 5i minus 9. So you could say that a sub 25 would be equal to 5 times 25 minus 9. It's not a recursive relationship. I don't need the previous one to get this. 5 times 25 is 125. And then minus 9. And 125 minus 9 is 116. So that's our 25th term. Little note. A sub 25 could have also been calculated by using the first term, a sub 1, and then adding 24 times the d, which would have been -4 plus 24 times 5. 24 times 5 is 120. 120 minus 4 is 116. Could have done it that way. Do I care which way you do it? Nope. Never ever. I care that you have a way to get it done. So therefore, S sub 25, that says the sum of the first 25 terms, which is the same thing as writing I equals 1 to 25, 5i minus 9, but we can only use S sub 25 if we know it's arithmetic. So now we just apply the formula. So I said I like to use the kind of split up version, the number of terms times the average of the first and last. So how many terms do we have? 25. Then times, now we average the first and last, so that would be -4 plus 116 divided by 2. 116 minus 4 is 112, so that's 25 times 112 over 2. Half of 112, that's what, 56? And then 56 times 25 is 1,400. That is a way shorter process than finding all 25 of those terms, listing them, and then having to go back and add them. And plus, when you're doing that much manual calculation, it gives you more of an opportunity to make a mistake in your calculator. So once again, very important formula to have memorized. You can memorize it blatantly like the green version, or you can memorize it more as a, in my opinion, concept, the black version, where it's the number of terms times the average of the first and the last. You have to show that it's arithmetic if you're not told that it's arithmetic in order to use this formula. Not all sequences are arithmetic. We have done many that were not. Anything that had like an I squared in it is not arithmetic. Anyone that has an alternator in it is not arithmetic. In general, if there's a denominator factor that involves I, it's not arithmetic. Let's try another one. Let's go the sum from I equals, give myself a little more room. (1 to 100), so the sum of the first 100 terms, that's a lot, I. I've seen this question in the media. I don't want to say the media necessarily, but I've seen this many, many times outside of a math class. What's the sum of the first 100 numbers? I don't know why. It's just a pretty popular question. So you go, okay, well, 1 plus 2 is 3, 3 plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21, plus 7 is 28. Well, this is going to get annoying, isn't it? So if you think this is arithmetic, because of the simplicity of the sequence, there's no i's in the bottom, there's no exponents, there's no -1 to the ends or anything like that, or -1 to the I. So maybe this is arithmetic. Let's try showing that it's an arithmetic sequence or series. So we get the first term, which is 1. We get the second term, which is 2. We get the third term. I don't know why I'm listing them horizontally this time. I liked listing it vertically. Which is 2. A sub 3 is 3. You can go to the fourth one if you need, but really you just need the first 3, quite honestly. And the difference between all of these is 1. Positive 1. Because that's the same, it's arithmetic, and D is 1. So all we really need is the first term, the last term, and the number of terms. To get the last term, so A sub 1 was 1. A sub 100, you can just use the sequence given to you. It's 100. If you really wanted to, you could add 1 99 times to 1, and 1 plus 99 is 100. So our series, I equals 1 to 100, for I, we showed that it's arithmetic, so we can write that as S sub 100. And that's going to be the number of terms, which is 100, times the average of the first and last term. So times parentheses 1 plus 100, all over 2. Well, that's 100 times 101 over 2. 2 goes into 150 times, so that's 50 times 101, which is 50/50. Could you have guessed that question? 50/50. I'm sorry, terrible joke. That's all I got. Terrible jokes. And one more problem. I am not going to do 11.3 today. I don't want to, it's another case of, I know I'd have to start an idea and then just kind of leave us hanging on edge and on a Wednesday at the end of the semester. Let's not do that. But we will be able to complete this section on Monday. Absolutely. The next section, that is to say. C, we're going to write this one out a little differently. I'm going to write A sub 1 is equal to -42. And then I'm going to say that D is equal to 7. And I'm going to say, what is S sub 66? This is a different setup. I have told you that it was arithmetic. How were we told? Because we said D is 7, and that's how we know it's an arithmetic sequence. Now, it might not be written as D, it might be using words. The common difference is 7. So it says the next term is the previous one plus 7. You can set it up recursively if you like. So the first term is -42, the next one would be -35, the next one would be -28, etc. You can certainly list out all 66 terms and then add them. I would never do that in my entire life. I would use the formula. But the formula requires that we know how many terms, which we do, 66, that we know the first term, which we do, -42, and that we know the last term, which we don't. So we need to find a way, wrong color, to get the last term. Well, if it's arithmetic, we're just adding 7 over and over and over and over and over. How many times are we adding it? 1 less than where we're getting to. Remember that formula from above, before. I think I just combined before and above in words. If a sequence is arithmetic, whatever term you want to find is the first plus 1 less of those D's. So it's the first term, A sub 1, and then, I wrote an A sub n. It should be A sub 66. That's the first term, which is negative 42, plus. Now we're supposed to find the 66th term, so we add it 65 times the d, which is 7. Actually, I'm not going to do that in my head in the interest of time. 65 times 7 is 455. So this is negative 42 plus 455. Multiples of 65 aren't too friendly. And then negative 42 plus 455 is going to be 413. So that is our 66th term. That is our last term. So the sum of the first 66 terms, also known as, actually, no, I'm not going to write it that way. There's no reason to. I don't actually have the sequence listed out in a formula, so if you wanted to write it out using summation notation, you'd have to figure out what it is. And it's negative 40, it's a sub 1 equals negative 42, and then a sub n equals a sub n minus 1 plus 7, because it's recursive, but there's no reason to write it out, so I won't. So this is the number of terms, which is 66, times the average of the first and last term. The first being the negative 42, the last being the 413, and then over 2 because we're averaging 2 values. So the 66 over 2 will make a 33. I'm going to reduce the 66 with the 2. 413 minus 42, that's 371. And if you multiply those together, let me get my calculator. You get 12,243. So you can get some really big numbers, especially if you add the first 100 or 1,000 or 10,000, or maybe even infinitely many terms of a sequence. Again, adding infinitely many terms of a sequence, this is a very common idea moving forward as you advance through calculus. Now, I think it's obvious if these numbers keep getting bigger and bigger, if you add infinitely many terms, well, that series just goes to infinity. If you add 1,000,000 plus 1,000,000,000 plus 1,000,000,000,000, that number is just going to get ridiculously large, and it does what we call diverge. If it converges, then it goes to a number. If it diverges, that means it goes to infinity. So what we are more interested in later math is infinite series that converge, that actually have a finite value, which means these sequences can't be getting bigger and bigger and bigger. They actually need to be getting smaller and smaller and heading towards 0. So this is an idea we're going to start playing with in the next section, but you know I love foreshadowing. So that was 11.2. That finishes the material. Again, that homework is available for any of you who came in a little late. Please know your Chapter 11 homework is available. Your Chapter 7 and 11 combined tests will start on Wednesday the 29th. I don't have a date for the review yet because I need to build it, and it is going to be a tighter schedule. It may be as late as Tuesday, but again, I know most of you aren't even looking at those reviews or the test until the last couple days anyways, because that's life. So I'm not going to feel bad for giving you a take-home test with 2 attempts where you could have your notes in front of you, since I have no control over that, and the review is just given a day early. So we'll call it there. Next time we'll go over 11.3. We may even have time to start our conic sections, depending on how things go. But have a great weekend. Get some work done. Get some studying done. Please email me if you have any questions. Remember, there's a discussion board set up on Canvas, and I don't think I have one for Chapter 11 yet. I'll set that up. But you can, if you have a Chapter 11 question now, just throw it in Chapter 10 or 7 or whatever it is. But I will try and go set that up this afternoon. Take it easy.